We're now going to go and begin a review of the first bits of physical applications. And in particular, we're going to be talking about ropes and springs in this part. So we're going to combine those into two. Okay, if you need a refresher on how these problems are worked out and in great detail, go ahead and watch the original videos from section 2.5. Our goal here is to review how to solve these problems, so it's assumed you already know. Okay, the idea is just to set up the integrals, and then we're going to do some basic stuff here. So let's begin with this one here. Let's draw the picture as we go along. So we have a spring here, okay? And the natural length of the spring is 12 centimeters. So let's go ahead and write that in here. This is 12 centimeters. And it requires 30 newtons of force to stretch it to 15 centimeters. So this chunk here, okay, that's an additional 3 centimeters here. And it requires 30 newtons of force to stretch it. Now, the main question here is how much work is done in stretching the spring from 12 to 20? Okay, so here that would be an additional 5 centimeters. And so how much work is done in stretching the spring from 12 centimeters to 20 centimeters? Okay, so let's recall Hooke's law here. Okay, remember for Hooke's law, when we're talking about the force done on a spring, it's proportional to its displacement. So let's try to work out some information here. And what I'll also do here is make sure that we have the units in line here because the canonical unit of length here in SI units is the meter. And we should remember that 1 centimeter is 1/100th of a meter. That's 0.01 meters. Okay, so let's go ahead and keep that in line there. Now, we're also going to need to set our zero position here because we only care about displacement from equilibrium. So we're going to treat this as x equals 0 in our coordinate system. And now we're going to go ahead and solve for the unknowns. So we know that the force on the spring, okay, here is 30 newtons. And in stretching it 3 centimeters beyond its natural length, okay, so we have 0.03 times k. We need to solve for k here. Okay, well, this is straightforward. We just go ahead and divide both sides by the multiplier there. And it takes a bit, but once you punch it in, you get that the spring constant K is 1,000 newtons per meter. All right, so now that we have our spring constant, we now know how to figure out how to get the work. So the work done in this process, the energy in this system, you're going to integrate from 0 to 0.08 because we want the length in meters here from the natural position, okay, from the equilibrium position. Okay, we're going to integrate our force function, which let's make that a little more clear here. Our force function is 1000x. Okay, and now we just go ahead and toss that in as our integrand here. And it's very simple, powerful work. Okay, so we get 1/2 of kx squared here. Okay, so we'll get 500x squared as our antiderivative. Evaluate that on the boundary, and using your favorite calculator of choice, you should get that we have 3.2 joules of work required to stretch that spring that distance. So very straightforward. You look at all the data that you have, build a force function, and integrate it. Again, here the integral is very simple, just in terms of polynomials where we just have to use a power rule. So now here's another one here. Okay, we have another spring. And it doesn't tell us its natural length, but we actually don't need the length here, okay? If we stretch it 1 foot beyond its natural length, so let's do that here. Okay, 1 foot beyond its natural length, the work done is 12 foot-pounds. Okay, now the question is how much work is required to stretch it 9 inches beyond its natural length? So in order to figure that out, let's mark that on our picture here. Well, note that our new distance is smaller than the given distance here. So I'm going to say that about 9 inches is right there. So I want the work done in stretching it 9 inches beyond its natural length. Okay. Well, we have a work already. We don't have a force function, but we can actually use stuff that we know. I know that the work done on an object, okay, is an integral from a to b of the force function kx dx. Okay, and if I use the power rule here, we get 1/2 kx squared evaluated on the boundary. And so this just gives us the change in energy. It looks like the change in kinetic energy, right? 1/2 kb squared minus 1/2 ka squared. And now here we're going to take a to be 0, that's the equilibrium position, and b is going to be 9 inches, okay, which remember, we want to put this in canonical units here. 9 inches, that's 3/4 of a foot. Okay, 9 inches, 12 inches in a foot, 9 divided by 12. All right, so now let's go ahead and put in everything that we know here. We already know the work done to stretch out a foot beyond. So we know that this work, 12 foot-pounds, is equal to the integral from 0 to 1 of kx dx. Okay, this one's pretty straightforward to do. Just 1/2 kx squared. Okay, but I get 1/2 k. Now notice that I have 12 equals 1/2 k. It's pretty easy to solve, right? Just multiply by 2. So our spring constant K is 24 pounds per foot. And now, just by using my little energy integral here, I can go ahead and plug in and figure out what the required work is. Okay, so the work done, okay, if I get the correct pen selected here, the work here is as follows. We're going to integrate our force function from 0 to 0.75. We know that our force function is now 24x dx, because K is 24. Okay, we go ahead and use our power rule here. Evaluate that on the limits of integration. And plugging in 0 gives us, 0, okay? And when we do all the work here, we get 27 over 4 foot-pounds. Okay, which is, let's see, 4 3/4, something like that. So 4.475 or something like that. It is 6. Nope, it is 6.75 foot-pounds. So very straightforward there. Okay, again, build from the data that you have, okay? And if you are just given work instead of a force, you can integrate the general relationship as I've done here. Okay, you can integrate the general relationship to get a relationship between the work done and the distances so that you can get a spring constant, okay, that stiffness constants. All right, now let's move on to a couple of problems with lifting stuff with ropes. Okay, same principles at play here. All right, so in this situation now, we have an elevator, okay, and it's suspended by a 200-foot cable. So this is my cable here. Okay, this is 200 feet of cable. And we know that the weight here of the cable is 10 pounds per foot. Okay, so get the units in the right place. So 10 pounds per foot. And this elevator weighs 1,600 pounds. Okay, now we want to figure out the work required to raise this 30 feet from the basement to the 3rd floor. Okay, so before we do, let's go ahead and make note of something here. Note that the weight of the elevator car does not change, but the weight of cable that's being pulled up at every stage does. Okay, so we have two forces that are acting here. We have the force done, okay, by gravity on the elevator car, and then the tension here that we're pulling up. So we're going to have two forces here. The force of the elevator car, okay, so the force of the elevator car here, okay, well, it's just its weight, 1,600 pounds. Whereas the force on the cable at any position x, well, remember how we have to do this, okay? We first decide where our 0 is going to be. Here, I'll make 0 the bottom. Okay, so this is x equals 0. Okay. And that means when we go up, we're increasing the x value. So positive is in the up direction as normal. Okay. Now, if I want to move this 30 feet, okay, well, then I'm going to go to some distance here, perhaps. But now let's think about, well, how much is remaining at each stage. Well, the total weight of the cable, okay, let's take that into consideration here. There's 200 feet of cable, and it weighs 10 pounds per foot, so we just multiply to get the total weight of the cable. And then if I move the cable a distance of x feet, I have lifted it I have lifted 10x pounds of cable. Okay. If I move it x feet, I've lifted 10x pounds of cable, just how the units work out. Okay, so now I can sum these two to get a total force function. Okay, 200 times 10 is 2,000. When I add these two, I get 3,600 minus 10x as our total force function. And this is the thing that we're going to have to integrate on our interval to figure out the energy required to move this elevator car. So the work done, okay, we're going to integrate from 0 to 30. Okay, that's this thing right here, 0 to 30. And our force function, 3,600 minus 10x dx. And this is just, again, very straightforward power rule stuff. So we get an antiderivative here. Evaluate this on the boundary. And if you check what's your favorite calculating device, you get 103,500 foot-pounds of energy required to move the elevator car the prescribed distance. Okay, so again, very simple, similar to springs. Okay, this one you just have to do a bit more thinking because you have to think that the weight, the amount of rope being pulled up at each stage is less, so that changes at every stage when you lift, but the elevator car has constant weight and so it does not change. So you just sum the two forces together. All right, let's go ahead and do our last one here. Okay, now we have a bucket on a 20-pound rope. Okay, so this rope weighs 20 pounds and it's in an 80-foot well, so 80 feet of rope. Okay, the bucket weighs 1 pound and holds 24 pounds of water. So the question is, how much work is done in lifting up one bucket full of water? Let's go ahead and highlight that there. So how much work is done in lifting up a bucket full of water? Well, the bucket is 1 pound itself and holds 24 pounds. So the total weight of the bucket here is 25 pounds. Okay, and of course there's no leaks here, so that weight does not change. Okay, well, I don't have a K, I don't have a stiffness constant, a tensile density here for the rope, but I can easily find it by dividing the weight of the rope by its length. So we'll take our K here to be 20 pounds by 80 feet. Okay, that's how the units work out. Pounds per foot. Okay, you do the computation there, we get a 1/4 pound per foot. Okay, so that's our spring constant K. That's our strength, our tensile strength. Okay. All right. Now we're going to do the same thing that we did for the last problem. We're going to decompose this into two forces. We have the force on the bucket. Okay, that does not change. Okay, so it's always going to be 25 pounds. Then here, the force on the rope. Well, I know the total weight of the rope, it's 20. And if I pull it up x feet, I have pulled up 0.25x amount of rope. And so this tells me the amount of rope remaining at any stage. All right, so now we sum the two together, the total force here. 25 plus 20 is 45, minus 0.25x. And I want to lift this entire thing out of there, so we're going to integrate from 0 to 80. So the energy required to work in our system, that's an integral from 0 to 80, okay, 80 feet of rope. Integrate our force function here. And once again, it's just a power rule. Okay, so we have 45x there. 0.25 is a fourth, so we have that divided by 2 for a power rule. We get an eighth x squared. Evaluate this on our boundary. And we get 2,800 foot-pounds when you do the evaluation. Okay. So, work with ropes and springs is really straightforward, okay? Start by drawing out your picture, list out your data, understand what the forces are at play, get a force function if needed, okay, or solve for the spring constant or tensile strength if you need to, and then it just all comes down to the power rule. So that's just a really straightforward refresher on how to handle these problems with ropes and springs. Okay, in the next section, we're going to do some more work, but this time we might be pumping some stuff out of a tank, and we may also be looking at the force on a side of a vessel. So it's all going to be about fluids next time. I'll see you in the next one.